Imagine a way to build a mathematical group that is completely unconstrained, one that lacks any preset internal rules. Traditional constructions, like the direct product, force interaction. They require elements from different groups to commute, imposing a specific relationship that wasn't there before. We need an algebraic blank canvas instead, a structure where no relations exist unless they are strictly required by the axioms of group theory. To understand how spaces merge without introducing hidden dependencies, we first have to learn how to combine groups without letting their individual rules interfere with one another. We are going to build this logic through two specific structures, the free product and the free group. Our guide for this construction is James R. Munkres Topology. This material marks the start of the text focus on the Seifert-Van Kampen theorem, specifically detailed here in sections 68 and 69. To define these spaces, we have to stop thinking about arithmetic and start thinking about algebra as a formal language of strings and words. By treating group elements as letters in an alphabet, we create the mechanical basis needed to track how paths and loops interact in a topological space. Let's start the construction of the free product with two arbitrary groups, G1 and G2. These groups must be disjoint. They cannot share any elements except for their respective identities. We define an algebraic word as a literal, ordered sequence of elements chosen from these groups. We simplify these into reduced words. First, any element representing an identity is struck through and removed from the string. Second, adjacent elements in the string cannot come from the same group. You cannot have two blue elements or two yellow elements side by side. A valid reduced word is simply an alternating sequence of elements from these distinct parent groups. To combine these, we use concatenation, literally pushing two words together to form a longer string. This often places two elements from the same group next to each other at the point where the words meet. When that happens, those adjacent elements multiply together using the rules of their original group, merging into a single element. If that new element is the identity, it vanishes. This pulls the remaining halves of the word together, potentially creating a new adjacency at the seam. This triggers a cancellation cascade. New adjacencies merge and vanish until the word reaches a stable, reduced state again. This continuous mechanical cycle of concatenation and reduction is what defines the mathematical structure of the free product. We can see this in action by looking at the free product of two simple groups, Z2 and Z2. If the first group is generated by A and the second by B, they combine into alternating strings like ABABA. Since these elements cannot commute and can't merge across groups, the word grows infinitely. Starting with two finite groups has resulted in a strictly infinite and complex algebraic structure. But what if we don't start with groups at all? What if we only have a raw set of elements, S? This is how we build a free group on a set S. We start with a raw set of objects with no pre-existing arithmetic. The issue is that a group requires inverses, which a raw set doesn't naturally provide. To fix this, we invent formal inverses for every generator in the set and add them to our alphabet. By treating these formal inverses as distinct letters, we satisfy the group axioms without introducing any other relations. Within this group, the only possible reduction is a generator multiplied by its own inverse. X times Y will never be the same as Y times X. This lack of internal constraints gives the free group a specific theoretical utility, called the universal mapping property. If you map the generators of S to any elements in an arbitrary group G, the free group structure uniquely extends that map into a homomorphism. This property shows that every group is essentially a quotient of a free group. The free group provides the most general possible structure that can then be restricted to form any other group. Let's compare these two ideas. The free product merges existing groups while keeping their elements from interacting in new ways. The free group builds a group from a set of raw elements by providing inverses and enforcing zero relations. In both cases, we succeed by moving away from arithmetic and treating group elements as typographic characters undergoing reduction. These algebraic constructions are the key to solving problems in topology. Managing these words is the exact mechanism we use to calculate the fundamental groups of spaces that are glued together. This structural algebra makes it possible to apply the Seifert-Van Kampen theorem to complex spaces. To see how these groups describe the geometry of the circle and the sphere, like, subscribe, and continue your study of Munkres.